Alright, in this video, we're going to be looking at multiplication and division of whole numbers. And we got a lot of things that we're going to cover. One is multiplication of whole numbers, the repeated addition model, properties of whole number multiplication, division of whole numbers, the division algorithm, relating multiplication and division as inverse operations, division by 0 and 1, and of course, order of operations. Okay, let's first look at multiplication of whole numbers. Multiplication of whole numbers can be modeled in several different ways. One of them is the repeated addition model, where multiplication can be thought of as repeatedly adding the multiplicand multiplier times. Example, 3 times 2, we can add the 3 2 times. That's repeated addition. The array and area model is where multiplication can be visualized by constructing an array of crossed sticks or a grid and counting intersection points or grid components respectively. Here's some visual representation. And then the Cartesian product model is going to be the multiplication that can be thought of in terms of Cartesian products. When we were talking about set operations, one of them was the Cartesian product. So we can think of that as multiplication as well. Let's start with the repeated addition model. If we have 4 groups of 3 brushes, we can use addition to put the groups together. When we put equal sized groups together, we can use multiplication. We can think of this as combining 4 sets of 3 objects in a single set. So here we got 4 sets of 3s. So 3 plus 3 plus 3 plus 3, which will be 12. So we can think of that as 4 times 3 is equal to 12, because we're adding 3 4 times. And using just using blocks here, we can represent 5 times 4. Okay, so here and on the number line, you can see that 4 is being added 5 times. So we're adding the 4, repeatedly adding the 4 5 times. That represents 5 times 4, which is 20. And also the block shows that 4 is used 5 times. So that represents 5 times 4, or 20. Also, the area and array models. Here, as you can see here, they're using intersecting lines, which are dots. So we have 4 rows of 5 dots. Each row has 5 dots. There are 4 rows of 5 dots, so that's 4 times 5, which is 20. And also the area, which is going to be these squares here. There are 4 rows, where each row has 5 squares in it. 4 times 5, which will be 20. Or you can count each individual square that's in this particular figure. The definition of multiplication of whole numbers is this: for any whole numbers a and n not equal to 0, n times a is going to be a plus a plus a, and so on up to the last a. That means there are n terms of a's being added together. That means if n is equal to 0, then 0 times any number a is 0. Alright, next we'll look at the Cartesian product model. Suppose you plan to take 2 web-based courses at your local college. You can take one of the following: World History, Ancient History. For your second course, you can take one of the following: Latin, French, or German. To show the number of different schedules you could have, you can use a tree diagram. Okay, the ways of designing your schedule are the result of selecting a history course from the set H, which is World History, Ancient History, and a foreign language, which will be L, Latin, French, German. And here's what the tree diagram looks like. we can design the Cartesian product H cross L using a tree. So, starting with the schedule, you could have world history or ancient history. And from that, for world history, you can choose Latin, German, or French. And for ancient history, you choose Latin, German, or French. Okay? And these are the 6 possible schedules that a student can have from those choices. And this is where the fundamental counting principle comes in. It tells us that the number of ordered pairs in H cross L will be 2 times 3 or 6. In other words, you can see we have 2 choices of a history and only 3 choices of a language. So 2 times 3 would be 6. That's the representation of multiplication using the Cartesian product. Okay, multiplication of whole numbers for finite sets A and B. If the number of elements in A is equal to A and the number of elements of B equals to B, then A times B is going to be equal to the number of elements of A cross B. So in this alternate definition, sets A and B do not have to be disjoint. The expression A with a dot in between it is, and then B, or we can write that as AB. Either way, that represents a product of A and B, and A and B are called factors. In other words, these 2 factors will give me an answer when you're multiplying. So A is a factor and B will be a factor. Now keep in mind that A cross B indicates the Cartesian product. Here we multiply numbers and not sets. Let's look at some properties of whole number multiplication. Pretty much these are the same for properties of whole number addition. One of them is the closure property, meaning that if A and B are whole numbers, then A times B is a unique whole number. Take 13 times 7, for example. That'll give you 91, which is a unique whole number because only 13 times 7 can give you 91. Commutative property of multiplication of whole numbers means if A and B are any whole numbers, then A times B will give me the same answer as B times A. In other words, the order does not matter. 5 times 3 is the same as getting 3 times 5. The associative property of multiplication of whole numbers is this. The grouping does not matter. If A and B are whole numbers, then if I group A and B together, the product of A and B, and then multiply by C, that's the same as grouping B and C together through multiplication and then taking that multiplied by A. So the grouping does not change the answer. The identity property of multiplication for whole numbers is this. There is a unique whole number 1 such that for any whole number A times 1 is equal to A, or 1 times A also will give you A. Then we have the zero multiplication property of whole numbers. For any whole number, if you take A, can be any whole number multiplied by 0, you're going to get 0. Or 0 multiplied by any whole number A will give you 0. Okay, now this is an illustration of the commutative property of multiplication. We got 3 rows. Each row has 5 boxes. That's 3 times 5, which is 15. This one has 5 rows. Each row has 3 boxes. 5 times 3 also gives you 15. So this is just an illustration of how the order does not matter when you're dealing with the commutative property of multiplication. Now the associative property is this. Let's say we have 3 stacks of boxes where you have 4 rows of 5 boxes. That's 3 times 5 times 4, where the 5 times 4 is in parentheses. And then this one, we got 1, 2, 3, 4 stacks, but then you got 3 rows, each having 5 squares. and then you're multiplying it by 4. Okay? So group the 5 and the 4 together and then multiply by 3. It's the same as grouping the 3 and the 5 together through multiplication and then multiplying it by 4. Okay? That's just an illustration of the associative property. Now, the distributive property of multiplication over addition is this. The area of the large rectangle equals the sum of the areas of the two smaller rectangles. Here we got the sum of 3 plus 4 boxes, and you got 5 rows of that. That's the same as this. 5 rows of 3 plus 5 rows of 4. Okay. Now, using letters for A, B, and C, if we got A with the B plus C in the parentheses, the distributive property tells us to distribute the A over the B and the C through multiplication. So this will be A times B, which gives me AB, plus A times C, which is AC. So A parentheses B plus C, using the distributive property, will be AB plus AC. And this also works for subtraction as well. Because if this was B minus C in the parentheses, and then you're multiplying it by A, you'll still distribute it, but it'll be A times B, which is AB, then minus A times C, which is AC. In this case here, B is greater than C. Because the commutative property of multiplication of whole numbers holds, the distributive property of multiplication over addition can be rewritten as this. The sum of B plus B and C in parentheses multiplied by A, that's the same as saying B times A plus C times A. Okay? And the distributive property can be generalized to any finite number of terms. That means if I have B plus C plus D in the parentheses, and that sum is going to be multiplied by A, I'll distribute the A over each and every term inside the parentheses. So you'll have A times B, that's AB, A times C, will be plus AC, and then A times D, which will be plus AD. When the distributive property is written as this, AB plus AC, which can be written like this, A parentheses B plus C, this is what we call factoring. Okay? We call that factoring because basically we're trying to find a common factor that's in both AB and AC. And in this case, A is the common factor. So the common factor will be on the outside of the parentheses. To get what's inside the parentheses, you take that common factor and divide that into each and every term. So AB divided by A will give you the B. AC divided by A will give you C. So in this case, the factors of AB plus AC are going to be the A, and the other factor will be B plus C. Let's say we want to use an area model to show that x plus y times z plus w is equal to xz plus xw plus yz plus yw. Okay, if we use the area model here, on the left side you can have x and y. Across the top will be z and w. Okay, and then you multiply each one of these to get what's inside the box. Like x times z will be xz, and then y times z will be yz, and then you got x times w will be xw, y times w will be yw. Okay, so using this area model, we can say that x plus y times z plus w will give you xz plus xw plus yz plus yw. Also, we can use the distributive property of multiplication over addition to show that x plus y times z plus w does give you xz plus xw plus yz plus yw. In this case here, we're going to use x plus y and multiply by z. which is this, and then x plus y will be multiplied by w to get this. Okay, and then we're going to use the distributive property again. X times z is xz, y times z is yz, x times w is xw, y times w is yw. And then if we use the commutative property, we'll see if we move these terms around, you have xz plus yz plus xw plus yw. All right, next we'll look at division of whole numbers. Okay, there are three models for division. One of them is the set or the partition model, and that's the set of elements representing the dividend, and it's partitioned into divisor number of subsets. Okay, because you're going to take those elements and then partition them into equal number of subsets. The missing factor model is this: is A divided by B is a unique. There is a unique number C, provided that B times some number C would give us A. And then the repeated subtraction model is where the divisor is continually subtracted from the dividend until only the remainder is left. Okay. Let's look at the set or the partition model as an example. Suppose we have 18 cookies and want to give an equal number of cookies to each of three friends, Bob, Dean, and Charlie. How many should each person receive? Okay, you're taking 18 cookies. Each one of them will have the same number of cookies. So here you'll see each one will receive 6 cookies. So 18 divided by 3 will give you 6. The missing factor model is this: if each friend receives C cookies, then the 3 friends will receive 3 times C, or 18 cookies. Therefore, 3C is equal to 18. And then we find out what number times 3 will give us 18. In this case, it'll be 6, because 3 times 6 gives us 18. So we have answered the division computation by using multiplication. Okay, definition here: for any whole numbers A and B where B is not equal to 0. A divided by B is going to be equal to C if and only if C is a unique whole number such that B times C is equal to A. Now the number, which is your A, that's your dividend. The B, that's the number after the division sign, is your divisor, and C is called the quotient. Now A divided by B can be written in 2 ways: A over B as a fraction, or in this particular way that we've been doing when we're doing long division, where you have the A inside this symbol here and the B is on the outside. Okay, the other model is a repeated subtraction model. Suppose we have 18 cookies and want to package them in cookie boxes that hold 6 cookies each. How many boxes are needed? Okay, 1 box is filled, then there are 18 minus 6, or 12 cookies left. Fill another box, then you'll have 12 minus 6, or 6 cookies left. The last 6 will fill the other box, so that means you have 3 boxes that were used. So 18 divided by 6 is going to be equal to 3. Okay, the division algorithm is this: given any whole numbers A and B with B not equal to 0, there exist unique whole numbers, which is Q, which is going to be the quotient, and R, the remainder, such that A is equal to B times Q plus R, where the remainder, which is R, is at least 0 but less than B. In other words, the remainder can be 0, but it cannot be bigger than your divisor. When it is divided by B and the remainder is 0, then that means that A is divisible by B, or that B is a divisor of A, or that B divides A. Okay? Let's say 123 is divided by a number and the remainder is 13. What are the possible divisors? let's see, 123 is divisible by b. Then that means from the division algorithm, 123, that's your dividend, is equal to some number b times q, which is your quotient, plus 13. But b has to be bigger than 13. And from the division of subtraction, from the definition of subtraction, b times q is going to be 123 minus 13, so bq must be equal to 110. In this case, you're thinking of an equation, so you have to subtract 13 on both sides to get bq is equal to 110. Now we're going to look for two numbers whose product is 110. When one number is greater than 13, okay? And here's the table showing a pair of whole numbers whose product is 110. We got 1, 110, 2, and 55. 3 can't go into 110 evenly. 4 can't go into 110 evenly. 5 can go into 110 evenly 22 times. And also 10 can go into 110 evenly 11 times. Now, from that table, we can see that 110, 55, and 22 are the only possible values of b, because each is greater than 13. So it'll be these three right here. And how can we relate multiplication and division as inverse operations? In this case here, addition and subtraction are inverse operations. Multiplication and division are also inverse operations. The multiplication and division has a relationship. From addition, we can relate that to multiplication because multiplication is repeated addition. Subtraction and division has a relationship. It's repeated subtraction. Okay? Because with division is simply repeated subtraction in this case. Okay, let's talk about division by 0 and by 1. We're going to let n be any non-zero whole number. Then n divided by 0 is undefined. Any non-zero number divided by 0 is undefined. 0 divided by any non-zero number, of course, is 0. 0 divided by itself is also undefined. And let me explain why. Any number divided by 0 is undefined. If you have 5 divided by 0, that means 0 times some number must give you 5. There is no number multiplied by 0 that's going to give you 5. So that's why division of any non-zero number by 0 is undefined. Okay. An order of operations is this: when no parentheses are present, multiplications and divisions are performed before additions and subtractions. The multiplications and divisions are performed in the order they occur, and the additions and subtractions are performed in the order they occur. I'm sure some of you remember the ever so popular mnemonic phrase, "Please excuse my dear Aunt Sally," as a way of memorizing the order of operations. The P is always your parentheses, which is your grouping symbol. Parentheses or grouping, any type of grouping symbols like brackets. The E is exponents or powers. Your M means multiplication. D is division. Keep in mind, multiplication and divisions are done in order from left to right. Addition for the A, and then S is subtraction. Add and subtract in order from left to right. Okay, that's the order of operations here. Okay, and that will conclude this particular video on multiplication and division of whole numbers.